George Efstathiou, who I'm getting to, who's the HFI survey scientist, and he's going to tell us about the results. So thanks very much, George.
Thanks, Paul. So just a word about the title. The weirdest sensation of my involvement in Planck was finally being able to talk about Planck to other people when we had the papers out in March. I'll start with my version of the history of the CMB. We've been fortunate enough to have a satellite designed to study the anisotropies of the cosmic microwave background in each of the last 3 decades, starting with COBE, which discovered the primordial temperature anisotropies, then followed by WMAP with their famous data release in 2003, and then 10 years later followed by Planck. And of course there are lots of little mammals here as well, the small-scale CMB experiments, suborbital experiments as well, that were, I think, critical to our analysis of the Planck satellite. So you'll hear about those experiments from Joe and from David Spergel. So what we released in March was the first 15 months of observations of Planck. So that's just over half the data taken with the HFI, the high-frequency instrument on Planck. The low-frequency instrument is still taking science-grade data. And so these show the maps of the first 15 months of the mission. So the low-frequency instrument covered the frequency range 30, 44, and 70 gigahertz, and then the high-frequency instrument covered the frequency range from 100, 143, 217, 353, 545, and 857. So all of the channels up to 353 have polarization information, and then these 2 channels, we just have temperature information. So one of the things that you can see from this plot, this set of maps, is, unlike the ESA press release, it's actually easy to see the primordial CMB anisotropies at frequencies 70, 100, and 143 above the galactic plane. You're seeing the primordial CMB anisotropies. And when you have this degree of frequency coverage, separating out the diffuse galactic emission on large angular scales from the galaxy is actually very easy, and that can be done to extremely high precision. You see at these high frequencies, we're not sensitive to the primordial CMB at all. These frequencies, the temperature maps, are essentially signal-dominated maps of dust emission, galactic dust emission, and the cosmic infrared background from distant infrared galaxies. So that's the data that we worked with, and then this is a foreground subtracted map as seen by Planck that is on the on your conference bag, and it's interesting, the wisdom of the Planck science team to decide to choose a different color table than the WMAP team, because otherwise this map would have looked just like the WMAP map at this resolution. Now, I got criticized a little bit at the press conference for saying that cosmologists would sell their children to get access to this map. But the reason that there's so much interest in this map is to see how much information we can extract out of this map of the primordial sky. Every bit of information that we can extract tells us something about the very early universe at the time that these fluctuations were generated. So we can look at the 3-point statistics. I won't talk about those here. Those are very high precision measurements from Planck. What I'll concentrate on are the 2-point statistics, the power spectrum from the primordial CMB fluctuations. So this is the power spectrum. So first, on the top panel, you see a conventional plot of L squared C of L. The blue points are the Planck results. I'll say a bit more about those in a minute. And the red line is the best-fitting 6-parameter standard lambda CDM model that I will call the base lambda CDM model. And that provides a very good fit to the observations. So the fit is so good. I mean, there are error bars on these blue points. The blue points are band averages, high multipoles in bands of width of delta L of 31. And then the individual power spectrum points, multipole by multipole, are shown by the gray dots. So on this type of plot, you can't really see anything. It's pretty uninformative. And so when you get to the precision of Planck, it's more instructive to look at residual plots. In this case, just the difference between the blue points and the theoretical, best fit theoretical model. And that's shown here. So again, the little gray points, the power spectrum multipole by multipole, and then the green line here is our analytic covariance matrix, the diagonals of the analytic covariance matrix that we used for the likelihood. So the Planck likelihood is a hybrid. It uses pseudospectra on the 100, 143, and 217 maps and all of the cross spectra that you can make from independent maps. So that's how that's constructed. And what I've done here is I've used a maximum likelihood way of combining the different frequencies to produce our estimate of the primordial CMB spectrum. There is no unique primordial CMB spectrum because you also have to solve for unresolved foregrounds, which I'll discuss in a minute. And so you know, to get the power spectrum, you have to do full likelihood analysis, assume a theoretical model, solve for the foregrounds, and then construct the power spectrum after you've solved for those parameters. The low multipole part of the spectrum, up to a multipole of 49, is computed from a component-separated map covering 87% of the sky. And this uses a Gibbs sampler to compute the likelihood at low multipoles. And then that's patched on to the high L part of the likelihood. So our claim in the first set of cosmology papers is that the base lambda CDM model provides a very good description of what we see, and that there's no evidence of any new physics apart from the physics involved in the base lambda CDM cosmology. So that's the claim, and I think the only thing that I would change from the first set of papers is that you see that over here at multipoles of about 1800, there's a little dip. That is probably an instrumental artifact. I'm not quite sure what I'm allowed to say about it, but Jean-Luc is here, so so he will field questions and give the appropriate official line. This has very little impact on cosmological parameters. So our claim is that the basic 6-parameter lambda CDM model describes the data. There's one problem here, that you can see that at low multipoles, the data sit low compared to the best fit theory. So here, I mean, here at these low multipoles, if we substituted the WMAP observations, you wouldn't be able to see any difference. The two experiments are in very good agreement. So that's a feature. There's nothing new here. There's nothing new here. These sort of dip features were seen in the very first results from WMAP. So I'll say a little bit about that later. So first, unresolved foregrounds. This shows the spectra at different frequencies from Planck. These are the cross spectra that we used for the high multipole likelihood from Planck. And you can see best fit theoretical model. And then at high multipoles, you can see that there are excesses. The excess is quite strong for 217, cross 217, shown by the green points here. And those excesses come from unresolved foregrounds. So you have to recover the information about early universe cosmology, we have to deal with these unresolved foregrounds. So the way that we deal with it is to have a model with lots of parameters. So we have templates for the thermal Sinyaev-Zeldovich effect from unresolved clusters of galaxies, from the kinetic Sinyaev-Zeldovich effect, from the cross-correlation between the thermal SZ emission and the cosmic infrared background. The cosmic infrared background expressed with amplitudes at the frequencies where it's relevant, Poisson point source contributions, and then various other nuisance parameters, relative calibration parameters between the different spectra. And then these betas represent the amplitudes of beam eigenmodes, because the beams are calibrated to finite accuracy. So we, we have eigenmodes that express the errors in our knowledge of the beams, and then we solve for coefficients. Now, in the actual likelihood that we released, the publicly released version of the likelihood, we marginalized over all of these and kept beta 101, the first beam eigenmode at 100 for the 100 cross 100 spectra, as a parameter, because that's the only one that actually showed any shift when we did analyses of the full likelihood. So there are a lot of parameters involved, and then you have your cosmological parameters in addition. And we have control. We have some control on these parameters because we have power spectra and likelihoods from ACT and SPT that Joe will talk about later, covering the same frequency ranges. So these are the ACT spectra at 148 gigahertz, 148 cross 220, 220 cross 220, and then SPT at 95, 150, 220. And what you can see here is that the high-resolution ground-based experiments, they cover much higher multipoles. They go up to multipoles of nearly 10,000, where you're totally dominated by the unresolved foregrounds. So we can use Planck on its own, solve for the foregrounds. We can use Planck combined with the high-resolution experiments, solve for the foregrounds and the cosmology. And as a general rule of thumb, if you see parameters shift between those two sets of analyses, with and without the high-resolution CMB experiments, then that indicates a coupling between the foreground model and the cosmology. Okay. So if we look at consistency of the Planck data, so at 143 gigahertz, we have 5 maps. And so we can compute 10 cross spectra from the 5 maps. And this shows the 10 cross spectra superimposed on top of each other. And this shows the RMS deviation from the mean of these 10 cross spectra. And then this shows, so this line here is not a theoretical model, it's just joining the dots. And this shows 0.2%, plus or minus 0.2% of the mean. And so these spectra are remarkably consistent. They're consistent at low multipoles to precision of about 0.1%. And in this case, the scatter is completely consistent with what we would expect from instrument noise. At 217, we have 6 maps. And so we can construct 15 cross spectra. This shows the same thing. In this case, the 217 channel is noisier. Again, the consistency is, multipoles up to about 1,000 is consistent to about 0.2%. And in this case, the scatter is about half noise and half coming from uncertainties in the 217 gigahertz beams. So we understand scatter in our data, and it's remarkably consistent. Here, power spectrum differences, so this shows the 143 cross 143 minus 217 cross 217 differences. The error bars here are coming from noise alone, and they're also in very good agreement, to within, with the scatter of 5 to 10 microkelvin squared. So the data is very consistent. We didn't use polarization in the first cosmology papers, but this shows the TE power spectrum from the 143 and 217 gigahertz channels. So those are shown by the blue points. And the red line isn't a fit to this data. It's the expected TE spectrum from the best fitting base lambda CDM cosmology fitted to the temperature likelihood. And that provides an extremely, extremely good description of what we see. And then this is the EE spectrum, again from 143 and 217. And as before, the red line isn't a fit. It's the expected EE spectrum from the temperature data. So we showed these in the paper, partly to show off. But also, there is an interesting science point as well, because in computing these spectra, we've assumed nothing at all about the unresolved foregrounds. So they're expected to be very low, so there's been no attempt to model or subtract polarized unresolved foregrounds, and the cosmology fits very, very well. So that's an additional check that the cosmological parameters are not particularly sensitive to the foreground model. So here are the parameters of the base lambda CDM model. And in many cases, the parameters are determined to an accuracy that nobody's interested in anymore. But some of these parameters raise some questions, and that's what I'm going to spend most of the rest of the talk on. We've seen the constraints on inflationary models, the tensor scalar ratio against the spectral index. So 1 and 2 sigma contours from Planck. And our 2 sigma limit on the tensor scalar ratio is about 0.11 when we combine with the baryon acoustic oscillation data. And really, this is not likely to improve until we have constraints, direct B-mode constraints on the tensor scalar ratio. With Planck, we've basically saturated what you can do on the tensor scalar ratio from measurements of the temperature and isotropies alone. So that you will hear from John later today about ground-based experiments to significantly improve on the tensor scalar ratio limits from Planck. So this picture compares Planck to WMAP. So the Planck 100 gigahertz spectrum is shown by the purple dots here. These computations were done very carefully using exactly the same sky cuts, point source holes, and so on between WMAP and Planck. And this is the WMAP combined V plus W spectrum. So it's computed on the same area of sky. But we've applied a calibration factor. So there's a relative calibration factor of 2.7% here. And with that calibration factor applied, then the WMAP and Planck points, this shows the residuals, they track each other extremely well. So these experiments are measuring the same thing on the sky, and so it's no accident that, if we cut back the sky coverage, the multipole range of the Planck likelihood to multiples of about 1,000 or so, we get the same, we recover basically the same cosmological parameters that WMAP find. But we find shifts in parameters when we use the full multiple range of the Planck likelihood. The difference in the relative calibration is not understood, and that's a subject of a lot of ongoing work. But it's something that I think should not worry cosmologists. Okay? So it's all to do with far side lobes, how much missing solid angle there is in the far side lobes, and so on. So I'm not worried by this discrepancy, and we are trying to track it down, but there is a real possibility that we'll never be completely sure what the cause of that is. So this is another part of the Planck analysis, the temperature analysis. This is the lensing potential power spectrum. So that's constructed from measuring the tri-spectrum in the Planck maps. So these show the lensing potential power spectrum points from Planck. And this band here, the line and the band, shows the plus or minus 1 sigma range of what we would expect from the Planck parameters for the base lambda CDM cosmology. And then this shows the residuals below. And so that's compatible with our measurements. There's no statistically significant evidence of any difference there. So the Planck-based cosmology fits the lensing power spectrum from Planck. So going back to this, let me say a little bit about this discrepancy here at low multipoles. We blow up the low multipole region. These are the Planck measurements. And then this shows, this band basically shows you the range of the power spectrum that's allowed by fits to the base lambda CDM cosmology. So the data hasn't changed from WMAP, but the precision of the theoretical constraints on the model has changed. And so you see that there looks to be, that the theory predicts a higher amplitude than the data. Now we tried to quantify this by computing a relative amplitude from the Planck likelihood, the low L Planck likelihood, a relative amplitude of the theory to the data when we cut the likelihood up to a certain value of L max. Okay, and so that's shown here. So if everything were fine, these points would be sitting around 1. And this is L max on the bottom. And this shows 1 and 2 sigma ranges. And so you see that there's a formally sort of 2.7 sigma discrepancy at a multiple of about 30. So is that indicative of a problem? I'm not sure, because this isn't a particularly high level of significance. And I mean, I don't know how to do look elsewhere statistics. My joke about look elsewhere statistics is if anybody uses them, then you should look elsewhere. So it's possibly indicative of some problem, okay, between the theory and observations, but I don't think it's by any means compelling. But the effect of this, it does pull parameters when you solve for cosmologies with extensions to the lambda CDM model, then this discrepancy in amplitude between the low multipole part of the likelihood and the high multipole part does tend to pull parameters. So one should be aware of that. So looking at other observations, this shows the ratio of the baryon acoustic oscillation scale divided by a combination of the angular diameter distance and the Hubble parameter of redshift surveys. So this dimensionless number is what galaxy redshift surveys determine, divided by the value expected from the Planck best fit cosmology. So here are the data points from a number of surveys, redshift surveys, and then this is the plus or minus 1 sigma band allowed by Planck. And that's an extremely good agreement with Planck. So we have very good agreement between Planck on the base lambda CDM cosmology and the baryon acoustic oscillations, but we started to find some tensions with other data sets. So this shows the magnitude redshift diagram residuals from the best fitting lambda CDM cosmology for a bunch of type 1a supernovae surveys. So this is a compilation produced by the Supernova Legacy Survey group. So what it shows is low redshift supernovae here, then Sloan Digital Sky Survey supernovae here, then their SNLS supernovae here, and then a few HST measured supernovae at high redshift. So, so this band shows the plus or minus 2 sigma range allowed by Planck. And you can see that it lies systematically low. And so what we found was a 2 sigma tension between the supernova data and the Planck data. And it does pull parameters. So for example, if you solve for dark energy with a constant equation of state, you get minus 1.13 plus minus 0.13 at 95%. So there's 2 sigma pull into the phantom domain. Planck, WP, by the way, is WMAP polarization. Planck, combined with the BAO data and WMAP polarization, gives us something that's perfectly compatible with the cosmological constant. Okay. So we were suspicious of that this might be an effect of systematics in the supernova data. And in fact, that was right, because just after we presented our results, the SNLS team told us of a campaign that they'd had to recalibrate the photometry from the SNLS sample with the SDSS sample. And in that analysis, what they found was an error in a color transformation for the SDSS-G band photometry. And with the correction of that error, this discrepancy goes away. Okay? So that revised data is not yet publicly available, but we can anticipate what it will do, because the supernovae are intrinsically more sensitive to W than this combination of data, is it'll pull W closer to -1 with a smaller error. Okay? So one of the results that caused quite a lot of debate internally to the collaboration and externally was the low Hubble constant from Planck of 67.3 plus or minus 1.2, compatible but a little bit lower than WMAP. And then these are direct measurements of the Hubble constant from Cepheid period luminosity relations, the old HST key project results, and then a number of other geometrical techniques that I won't describe. So is that a significant discrepancy? It's a 2.5 sigma discrepancy. If you add the Hubble constant to Planck, you get pulled towards new physics, particularly in the neutrino sector, at the sort of 2.5 sigma level. So is this right? Well, I've spent some time looking at this. So this is my analysis now of the Reset-Al Cepheid data. So, so the way this works is, so these are observations of, these are dust-corrected magnitudes in the H-band measured by, with the Hubble Space Telescope, plotted against the period of the Cepheids. All of these red Cepheids are accepted in the fit. The blue Cepheids have been rejected from the fits, okay, because there are oddball objects. They may not be classical Cepheids. There may be problems with crowding in the photometry, even at the resolution of the Hubble Space Telescope. Maybe Cepheids in binaries. So there are many reasons for why you will get outliers in this type of analysis. And so, so you need to use a rejection algorithm to reject outliers. And one of the things that I noticed about the Reset analysis was their rejection algorithm favored measurements with large errors that lay close to their relations. So they get low chi-squareds and so on. So I didn't think that was very good. So I did develop my own. The blue points are Cepheids that are rejected by both Rees and by me. The blue points are, the open symbols are Cepheids that are accepted by me but rejected by Rees. Okay, and then the red ones are accepted by both of us. And so the way this works is that you have observations in the period luminosity relation in something that you know the distance to, in this case using NGC 4258, which has an accurate megamaser distance. And you compare the period luminosity relation of this object with the distance that you know to more distant galaxies with supernovae. So that gets you the distances to these galaxies, and then you use the supernovae, you match those on to more distant supernovae and determine the Hubble constant at large distances, free of the Hubble flow. So the precision that you have to do this to, the dotted lines here show a plus or minus 2 kilometer per second shift in the Hubble constant. So you've got to get these 0 points accurate to that sort of level. Okay, so here are the results of my analysis. Just after the Planck results came out, there was a new maser distance to NGC 4258. So the new maser distance changed the distance to 7.6 megaparsecs from 7.23, which is what Rees et al. Assumed. So that instantly lowers the Hubble constant. And so these are the results using NGC 4258 as an anchor distance for different assumptions of different priors on the slope of the period luminosity relation and the metallicity dependence of the relation. Okay, so no priors, then a weak prior, strong prior, so on. I won't go into the details. But you see the results using NGC 4258 were all stable at around 70.5 plus or minus 3, something like that. So that's perfectly compatible with the Planck value, no significant tension. Then you can also use the LMC, Cepheids in the LMC, as an anchor. And I've used a revised new eclipsing binary distance to the LMC. And these are the numbers that you get. And now what you see is that the numbers change a lot depending on what sort of prior you put on the metallicity. And Wendy's here, and Wendy would argue that the metallicity dependence is very weak, okay, in H-band, from an analysis of metallicity dependencies of LMC Cepheids. But the data with no priors pulls you to low values of the Hubble constant. There are definitely in the Rees data low metallicity Cepheids that are subluminous compared to the rest. And so you pull out a metallicity dependence that is actually discrepant with what Wendy finds. So that's the problem with using the Large Magellanic Cloud. Then the Milky Way parallaxes give a high value. Okay, and you can see that now there is tension between this value and the Milky Way parallaxes. And in fact, you can use the Milky Way parallaxes to get a distance to NGC 4258, and then that becomes discrepant at nearly the 2 sigma level with the new megamaser distance. So the data is not all brilliantly self-consistent. Okay, so just to show you, these are the Milky Way Cepheids with parallax measurements. These are the distant supernova host galaxy Cepheids. And you see that these are all low period Cepheids. There's only one that overlaps in period range with the supernova hosts. And you slightly change the prior on the slope, and the Hubble constant goes down a lot. So what are we to make of this? If it were up to me, I would split the H0 measurements into an NGC 4258 prior and something else. Okay, they differ. Then this shows parameters from Planck. The green points are Planck plus WMAP polarization, and the blue points were our favored data combination of Planck plus WP plus high L plus BAO. For different models, so this one has massive neutrinos plus curvature, then additional relativistic species, neutrino-like particles, N effective plus sterile neutrino mass, N effective plus M nu. The interesting thing about this is that, and this is a point that I think is not actually properly appreciated even within the Planck collaboration, is that these data combinations are not biased against new physics in these models. But yet there's no pull towards high values of the Hubble constant. Okay? So unless there's a problem with these data, then the conclusion is that there's no evidence for any new physics in the neutrino sector from Planck. Everything is compatible with the NGC 4258 distance, and there's tension with the Milky Way plus the LMC. And I think that's a fair reflection of where we are. There are other problems. The sigma 8 problem from clusters from Planck detected from the SZ effect, which give a constraint on the amplitude of the fluctuations against omega matter, give plus or minus, give 1 and 2 sigma contours shown by the blue lines, and constraints from the Planck primary CMB that give a higher value of sigma 8. That's also a sort of 3 sigma-ish discrepancy. Is it caused by problems in the physics of clusters that we don't properly understand, in particular the relationship between the mass of clusters and their SZ flux? So a number of people have written papers since we released the data on evidence for new physics coming from that sigma 8 discrepancy. So here are some plots from a paper by Batty and Moss. So this shows the lensing potential power spectrum from Planck as the green points, and then SPT as the blue points. And an interesting thing from this is that is there a tension between the SPT data and the Planck base lambda CDM parameters, okay, which we haven't looked at. And then this shows the weak lensing shear spectrum from the CFHT lensing survey. These results came out too late for us to analyze in the March papers. And again, the prediction from the base lambda CDM cosmology. And so these points sit low. And so are these discrepancies symptomatic of a problem with sigma 8? And that's the problem that Batty and Moss asked. And then this detailed table here of different combinations of data. I'll be quick in the analysis here. So 2 sets of models analyzed active neutrinos and sterile neutrinos. So this is just masses of active neutrinos. So with Planck plus the BAO, you get a 2 sigma upper limit of 0.25 eV on the mass of neutrino. When you combine with the lensing, and that is all of the lensing, CMB lensing plus CFHT lensing, plus the SZ constraints from Planck, then you find possible evidence of a neutrino mass. But what you also see is that this value is, outside the 2 sigma range of this data combination. So maybe it's right, or maybe it's reflecting problems with the lensing and SZ data. When you add sterile neutrinos, you see a similar thing, when you add the lensing data, you start to see evidence of a sterile neutrino mass. And when you add in the SZ constraints on sigma 8 and omega m, then that becomes a nearly 3 sigma evidence of a sterile neutrino mass. But again, this value is 2 sigma away from the limit set by this data combination. So again, possibly reflecting tensions in the data. This is reflected in the likelihoods. The CMB and the BAO likelihoods do not want any new physics. The new physics is coming entirely from the lensing and the SZ. Okay, so I've got to the end. I sent some of this stuff on the Hubble constant work to Adam Rees, who said, I think you're trying too hard to reconcile the data with Planck. And I refute that charge completely. He also said that tension is healthy. It's the only way we can find new physics. And I agree with that. But tension can also indicate crap in the data. So theorists should beware of astrophysical data. It's less clean than the CMB. And if it were up to me, I would not allow theorists to use H0 or supernovae if you don't know what a distance modulus is. So for observers, convince us that tensions are not caused by systematics in your data. And that applies equally to us on Planck as it does to other observers. And so I welcome any evidence of problems in the Planck data or unusual things that we need to look at in more detail. And always be suspicious of papers that combine lots of different types of data. If you throw everything into the mix, then it's very, very likely that you will get crap out. Okay? So that's what I really wanted to for you as an audience to come away with. On extended lambda CDM models, I really strongly support what we did in the Planck papers, thank you, of using Planck plus the baryon acoustic oscillations, because this is a very simple geometrical measurement to set constraints on extended models. And there's no evidence from these data for any new physics beyond the 6-parameter lambda CDM cosmology. And then finally, Planck is a large collaboration, and I want to acknowledge the contributions from all of these institutions. This poor institution has a very bad logo, but it's been a large effort, so I'll end there. Thank you.
Right, are there any questions? I'm sure there's some. And remember to wait for the microphone if possible. Okay.
Quick question. The Milky Way SFH is crappy data or good tension? The Milky Way discrepancy with SFH, the Milky Way SFH discrepancy of the Hubble constant, crappy data or good tension?
Well, it could be a number of things. I mean, there's this lack of overlap in the period luminosity relation. That will be killed by Gaia, okay, because Gaia will measure many thousands of galactic Cepheids with accurate parallaxes and so on. But even then, you've got to worry about differences in crowding, because these Cepheids are observed in crowded fields. And there are very substantial crowding bias corrections involved in these measurements. You have to worry about differences in photometric systems and so on. So there are a number of issues. The reason that I favor this comparison is because when you're doing this relative comparison, you're not so sensitive to differential crowding differences. You're not sensitive to metallicity differences. And even the rejection algorithms they're doing basically the same thing. Okay, so that's why I think that inherently this is probably the safest. So, yeah.
We had a question from Ofa.
George, it's a generic question about nuisance parameters. You know, it's something we all struggle with in various cosmological data sets. Should we feel comfortable that we fit the whole universe with 6 parameters and then add hundreds of nuisance parameters to the analysis?
Well, why? Why do you say that? I mean, you know, that's the real world. You have to deal with the real world as you find it, not as you would like it to be. So you have to deal with it.
Well, ideally, you'd like a physical model for nuisance parameters, right? This would be the ideal scenario.
Mm-hmm.
When you don't have it, yes, you have to put hundreds of parameters, but then the question, you know, this parameter degeneracy, and the question is of stability.
Yeah. Well, we can.
Stability of the result.
We can study that. I mean, that's one of the reasons that I think it's really good to have the high-L experiments because Planck on its own is not very constraining, particularly for minor foreground parameters like the kinetic SZ and so on. What happens when you use the high-L experiments is that you pin down those parameters and it leaves basically point source amplitudes with a spectrum that we know, free for Planck. And it doesn't make very much of a difference. They don't couple strongly to the cosmology. But if you go to models which are highly degenerate in the CMB, particularly with N effective, then you start to see couplings come in. Okay? And you know, that's the only way out of that is to improve the polarization measurements to the point where they become really very competitive with the temperature measurements, and that will happen. And then you have wonderful sensitivity with a lot, you know, to cosmology with a lot less sensitivity to foregrounds.
Time is short, but we have another question over there. Yes, thanks.
Just to follow up on the question, George expects me to disagree with him, but I don't. But the Milky Way data are not crap. I think that's an unfair characterization. The parallax data are a big improvement over what there was before. But and where I really agree with George is Gaia is going to make this better, including the period range over which the Cepheid period luminosity relation can be carried out to. And I think, and also for the R Lyrae, so there'll be an independent check of the systematics. And systematics are the name of the game. But what's really changed is there are now spectroscopic abundances for Milky Way and LMC Cepheids where you can look at some of these systematics in a lot of detail. And I think these tensions are healthy, and systematics is the name of the game. But there's a huge amount of data coming down the pipe which will address these issues.
Yeah. I mean, that's the thing that, you know, one of the most important things that I learned from doing that study was that you know, the Reese data has a metallicity dependence in it. That data has a metallicity dependence in it, and it's actually quite extreme. So it's almost certainly not right.
Yeah, I mean, the other thing is where there are crowded regions, it's sometimes hard to disentangle metallicity from crowding effects because they're coupled.
Yeah.
The inner regions are more crowded and higher metallicity.
Right. I think, oh, well, all right, one last question, okay. And Joe, could you start setting up if that's all right? Sorry.
George, so one way to resolve the low L discrepancy and also sigma 8 discrepancy is to actually lower optical depth, because that will force you to lower sigma 8 as well. And have you looked at that for low L? You're relying entirely on WMAP.
Yes,
there,
yes.
right?
We're relying entirely on WMAP, and we're still reliant on WMAP. So, but I think that the change that you would need to solve that problem requires, you know, just too large a change in the optical depth. You only have, you know, e to the minus 2 delta tau to play with.
For low L, all you need is change of 0.02, right? That's all you need.
Well,
that's 1.5 sigma.
well, we can talk about this, but I thought it was just probably too large to blame it all on optical depth. But hopefully we will see.
Okay. Okay, well, let's thank our speaker again.